All right, welcome to video 3.2 from chapter 3, talking about stoichiometry, which is going to be one of the most important techniques and concepts to take away from this entire class. We're going to use it pretty extensively. So stoichiometry really gets back to this original question that I mentioned at the beginning of the video 3.1, which is how do we take, say, the burning of steel wool in air and take a mass of the steel wool and then use a balanced chemical reaction to predict what the mass of the ultimate reacted product would be. In other words, we took some amount of iron and we reacted it with oxygen to make rust. And we knew that we had a certain amount of grams of this stuff, and we want to know how many grams of this do we have left over. That's what stoichiometry allows us to compute. So we're really relating the mass of reactants to the mass of product, and our key here, this part that allows us to convert between, that's through the use of the balanced chemical reaction, which is why we started with that in the video 3.1. All right, let's do this with an example. So I've got written up here this molecule C2H4, which is also known as ethane, mixed with HCl, which we know is hydrogen chloride or hydrochloric acid gas. So these are both in gas form, and they produce this C2H5Cl or ethylene chloride mixture. So when we look at this reaction, the first thing we should ask ourselves is this balanced? So pause the video for a second and convince yourself how to balance this reaction. Well, if you looked at this, you should identify that the reaction is balanced as written. So what does this actually mean? We have this balanced reaction. What do the numbers mean? Because we don't have any numbers in front of these or coefficients, but we could imply that really there's a 1 here, there's a 1 here, and there's a 1 here, which what do these ones actually mean here? It's really important that we think about this. Well, it actually means two different things, and it's useful to think about these in different ways depending on the question that's being asked. The first thing that it means is at the molecular level. Literally, what you have happening is you have a C2H4 molecule. We'll just draw it like this. So this is C2H4. You have one of those, and that's going to literally collide with an HCl molecule. So these two things are going to run into each other, and when they do that, they're going to produce one new unit of this, we'll call this the C2H5 or the ethylene chloride gas. So this is happening at the molecular level. Remember, there's probably trillions of these reactions that are occurring simultaneously, but that's what this balanced chemical reaction tells us, is that there's 1 to 1 to 1 of these, and that's what's happening. If we were to zoom in with the world's greatest microscope to see this happening in real time, we'd see these collisions happening, and for every one of these that collide with each other, we get one of these. That's the sort of first meaning, the literal meaning of those coefficients in a balanced chemical reaction. That can be helpful to think about, and definitely when you get to Chem 108 and you think about kinetics and kinetic molecular theory, you're going to be thinking about things from the molecular level or the molecular point of view, and this sort of relationship is going to be really important. But in a lot of other contexts, we want to think about these things at the mole level, and the reason why is because we're often not thinking about reactions with one molecule reacting with another molecule. We're thinking about bench scale or lab scale reactions. And at that level, we're thinking about trillions and trillions and trillions of molecules at the mole level. Remember, 1 mole is equal to 6.022 times 10 to the 23rd of whatever that object is, whether it's a compound or a molecule. And so these coefficients here, this one, and this one, at the same time, they literally mean that 1 mole of this C2H4 is going to react with 1 mole of HCl to produce 1 mole of C2H5Cl. Those are two totally different meanings, and they may feel like semantics, but they have huge implications, because at the mole level, we're talking about huge numbers of molecules as opposed to the molecular level. And so we often want to think about these things at this very large scale. So that relationship, knowing that 1 mole is reacting with 1 mole is reacting with mole, that's really useful in sort of an abstract sense, but what does that actually do for us at the sort of lab or the bench scale? Well, we need to think about, well, what does 1 mole of C2H4 actually weigh? Because that's what we'd actually be weighing out in the lab, right? If we wanted to do this reaction, we wanted to be efficient about it, we wouldn't want excesses of either of these two things. We want 1 mole of this and 1 mole of this, or 2 moles of this and 2 moles of this. We wouldn't want 1.5 and 1. Otherwise, one's going to run out and we're going to be left with excess. If you think about that at the industrial level, maybe you're making a really expensive pharmaceutical drug, you don't want to waste a bunch of stuff. You want to know exactly what the balanced proportions are, and then you want to weigh out exactly the amounts of each of those so they react what we call in a stoichiometric way, in a way that's defined by their balanced chemical reaction. In order to do that, we need to know, well, how much in grams is that 1 mole and how much in grams is that 1 mole. And by doing this, we'll also be able to answer, well, then how much in grams of this stuff would we produce, knowing that they react 1 mole to produce 1 mole. In order to get to this part from moles to grams, we need to introduce this new concept that's actually really similar to a concept we already introduced, and it's called molecular weight. So molecular weight is the average mass of that particular substance, and it's the sum of the individual atomic weights. Remember, the atomic weight was that portion on the periodic table, which was the weighted average of all the isotopes of that particular atom. So we had something like carbon, which had 6 protons, and then it had a weighted average of 12.001. And we said that that number was the mass of 1 atom of carbon, but it also was the mass in grams of 1 mole of carbon. So if we have, say, an example, let's do this in green. Let's do C2H4, which is the compound that we started with up here. If we have C2H4, if we want to compute the molecular weight, all we do is add up the individual atomic weights for each of these individual elements that comprise the C2H4 molecule. So we'd have 2 carbons, which we could say is 2 times 12.011. Sorry. Gives us roughly 24. I won't do the math exactly here. And we have 4 hydrogens, so that's 4 times the mass of hydrogen. We look at the periodic table, it's 1.008, so that's roughly 4 in this case. I'll put a squiggly there to say that it's approximately. And so the molecular weight of C2H4 would be around 28 grams per mole. Or we could think about this just like we did for the atomic weight, where this would also be the weight of a single C2H4 molecule, but not in grams per mole, in atomic mass units. So if we wanted to think about a single C2H4 molecule would weigh 28 AMUs, or atomic mass units. If we want to think about a mole of these, which is 10 to the 23rd of them, there would be 28 grams that we would have to weigh out for every 1 mole of those. Okay, so pretty straightforward. So we can do the same thing. Let's scroll up here. Let's do the same thing for HCl. We'll do that over here. So HCl, we've got 1H, which is going to be 1 times roughly 1, gives us 1. And we've got 1Cl, which is going to be 1 times roughly 35.5. I'm not being cautious with sig figs here just for illustration purposes, but in reality we'd want to keep track of all of these. I'm just trying to move quickly through this. That's 35.5. So our sum here is 36.5. That's the molecular weight of HCl. And we can do our last one here, so C2H5Cl. You might want to pause the video, make sure you add this up correctly yourself. This is going to produce a molecular weight of 64.5 grams per mole. Okay, so that's a good starting point. Now we know how many grams each one of these, so this is grams, we know how many grams 1 mole of each of these substances weighs. And they should be different, right? Because they contain different amounts of protons and neutrons. And so HCl 36.5 grams makes 1 mole, but C2H4, it's actually a lighter molecule, so you only need 28 grams to get the same number of molecules. Because remember, 1 mole is still the same number of molecules, 6.022 times 10 to the 23. Okay, so take a couple minutes here and pause the video and try to figure out what the molecular weight is of NaHCO3. We call this sodium bicarbonate. This is also known as baking soda. So pause the video and think that through for a second. Okay, so if we add up the individual atomic weights, we have sodium, which weighs 22.989. Hydrogen, we got one of those, it weighs 1.00. Carbon is 12. And oxygen, we have 3 of those at 16 apiece. We add all those up and we get 83.989 grams per mole. That's the molecular weight of the sodium bicarbonate compound, which, remind ourselves, means 2 different things. That is literally how many grams 1 mole of this compound weighs. So you'd weigh out roughly 84 grams of that to get a mole of it. But it simultaneously means that one individual formula unit of NaHCO3 weighs 83.989 atomic mass units. So we can think about it either at the molecular or the mole level. Okay, so let's do a real example. So now that we know how to determine the molecular weight, which is really the key to being able to convert between moles, which is sort of a useful practical thing that we use in lab and also comes from balanced chemical reactions, to grams, which is the thing that we actually weigh out. And so that gets us to the real question of stoichiometry. As I mentioned at the beginning, how do we use the mass of a reactant to produce or compute what the mass of the expected product should be? And so we've got an example here which states how many grams of NaOH, this is also called sodium hydroxide, are needed to fully react with 25.0 grams of Cl2. And again, I don't have a subscript, so this is actually Cl2 gas, which is chlorine gas. So we need to use this idea of stoichiometry, a balanced chemical reaction, and then we need to use molecular weights to go between moles and grams. Okay, so let's break this down into steps. So the first thing we want to do is balance the reaction. So if we balance the reaction, we know that we have NaOH plus Cl2 gas, and that is going to produce, and I'll just write out the full chemical reaction. You wouldn't have to know this. This would be given to you. You don't yet have the intuition to know this. NaOCl, which is sodium hypochlorite, that's also known as bleach, plus NaCl, which is table salt, plus water. Okay, so this is, at this point, the unbalanced chemical reaction. We'd go through this systematically. We won't here. I'll just balance it for you. We can go here and just have a 2-1, and it turns out that this whole thing is balanced. You'll want to pause the video and convince yourself that's true. Okay, so what do these coefficients mean, right? Again, this 2 literally means that we have 2 of these formula units colliding with every one of these at the molecular level to produce one of these, and one of these. That's the molecular picture, which is useful, but not as much as the molar picture, thinking about it from the mole terms. So this also means that we have 2 moles of this reacting for every 1 mole of this. Let's just be explicit here, so 1, to produce every 1 mole of this, 1 mole of this, and 1 mole of that. Okay, so let's use these molar ratios because really they're telling us the proportionalities of these molecules and how they actually react at the molecular level. So we know how they react in molar space. We know 2 moles react with 1 mole. But be clear, be absolutely clear that that does not mean that 2 grams of NaOH react with 1 gram of Cl2, right? Because these 2 things have different molecular weights, and so their mole to gram ratio is not the same. So this is not, absolutely not true, which is the basis of stoichiometry. How do we actually convert these 2 things? So I'm going to erase this for a second, get rid of this too, and let's think about how we want to do this stoichiometry. Okay, so the first thing we need is the key. Well, I'd say actually the first thing we have is the key, which is telling us the molar relationships of how these things actually react. But we need to be able to go between moles and grams interchangeably. And in order to do that, we need the molecular weights of the key compounds. And really, we're being asked to think about NaOH and Cl2. So we don't need to know the molecular weights of everything unless we were being asked about those things. So let's start with figuring out the molecular weight of NaOH and of Cl2. So NaOH, pause the video and make sure you can add this up, otherwise I'll just give it to you. So the molecular weight of NaOH is, let's write molecular weight equals 40 grams per mole, and Cl2 here is going to be, let's see, what do we have for Cl2? 70.9 grams per mole. Okay, so this is our second key. So first key, balance reaction. 2, molecular weights, which we have for the species that we're interested in. Now we need to do some stoichiometry, which requires dimensional analysis, just to relate these things through. So let's scroll up a little bit here and start this process. So let's do some stoichiometry. And let's just start with the 25 grams of Cl2 that we know. So we have 25.0 grams of Cl2, but there's no gram to gram relationship in a balanced chemical reaction, right? This is moles to moles, which is not grams to grams. So that means we need to get to moles. So we need the molecular weight. We'll do this dimensionally. So we've got 25 grams of Cl2. We know that the molecular weight is 70.9. So for every 70.9 grams of Cl2, that is also equivalent to 1 mole of Cl2. Let's dimensionally get rid of these units. So once we operate this, we will have an answer that is 0.353 moles of Cl2. Okay, that's a good start. Now we know how many moles of this thing we have. And we're being asked if we've got 25 grams of this stuff, which is the same as 0.353 moles of it, how many grams of NaOH are needed to fully react with that? Well, we know they react in a 2 mole to 1 mole relationship, and we know that we have 0.353 moles of this stuff. So we could sort of think about this intuitively, right? If we know that we need 2 of these for every 1 of these, and we actually have 0.353, then that means we're going to need probably about 2 times that amount of NaOH in moles. We can do this dimensionally. So let's go back down here, and I'm just going to keep going on this value that I first computed, and I'm going to use the molar relationship to compute this. And I'm going to say, well, for every 1 mole of Cl2 that reacts, I've got 0.353 of them. For every 1 mole that reacts, how many moles of NaOH are required? Well, 2, based on this balanced chemical reaction. So 2 moles of NaOH are required. If I then get rid of my units dimensionally, I'm going to be left with 0.706 moles of NaOH that were required to use up all 0.353 moles of Cl2, or the 25 grams that we started with. That's not the final answer, because we're being asked, well, what mass in grams of NaOH, remember grams here of NaOH, do we need to fully react with these 25 grams? We know that that's 0.706 moles, so what's the last piece of information that we need? Well, we already have it, right? We just need that last conversion factor, which goes between moles of NaOH and grams of NaOH. That's the molecular weight. And so I'm going to add that on here dimensionally, and I'm going to say that we have 0.706 moles of NaOH, and for every 1 mole of NaOH, that's equivalent to 40.0 grams of NaOH. Let's get rid of these moles of NaOH, and I'm going to slide this screen up a little bit so that we can see. And if I compute this with my calculator here, I get 28.2 grams of NaOH. So if we go back to the original question, the question was we had 25 grams of Cl2, and that was going to react with some unknown gram of NaOH, and we knew that it was going to react in a 2-to-1 molar way, and we used stoichiometry to compute what that actual mass was. So if we take an Erlenmeyer flask and we fill it up with 25 grams of Cl2, which would be gas, so we'd put a stopper in here, and we fill that up with a bunch of Cl2, we would then need to add exactly 28.2 grams of NaOH, which is a solid. We'd shake this thing up back and forth and let it react for a while, and what we'd be left with is 100% all of the products that we had expected to produce, and we would have none of the original Cl2 or NaOH left over because we would have reacted them in exactly the ratio that they needed to react. That's the benefit of knowing stoichiometry, is we can be really efficient about how we conduct reactions, meaning we don't have any excesses. In some cases we will have excesses, and that's going to bring us to our next topic of limiting reagents.